I'm the Associate Chair of the Department of Computer Science. And on behalf of our chairman and the rest of our colleagues, I want to welcome you to this important event, Student Security Day. I'm sorry I was not able to be with you from the beginning of the day, but I was briefing the President because one important development in the general area is also that the University of Houston was selected as a center of excellence in borders, trade, and immigration. And this center of excellence basically contributed in the general idea of flows, global flows, flows of people, goods, and information. And Houston Security Day, if I understand it, it's about the flows of information, correct? So I'm here to say, so I'm here to welcome you, everybody, and I'm looking forward to hear more about the presentations.
Thank you, Alex. So let's get started. So it's a great pleasure and distinct privilege to welcome and introduce Dr. David Marchek, who is a principal scientist at the Naval Surface Warfare Center. And David has a PhD from George Mason University in computational sciences and informatics. His research projects are in computational statistics, graph theory, network analysis, pattern recognition, and please note, everybody, computer intrusion detection, because we had a module presentation on that, so it's very relevant, and also image analysis. He's a fellow of the American Statistical Association and also the Association for the Advancement of Science, and an elected member of the International Statistical Institute. He's an associate editor for the Journal of Computational Statistics, and he has authored 2 books, one of them on intrusion detection, a statistical viewpoint, and random graphs for statistical pattern recognition. Without further ado, David, it's all yours.
Thank you. It's a pleasure to be here. Thank you for inviting me. I will start by saying that everything I say here is my personal opinion. I am not speaking for the government or any other organization. And I probably won't be able to make the little box.
Yeah, it is.
That was the wrong one. Yeah. Something happened. Well, maybe I'll figure this box out by the time we get done here. So I'm going to talk about what I think everybody should know. And basically what everybody should know is obviously what I know. So that's the way my bias tends to read. So I'm going to talk about data issues, variations, various ideas on processing the data, and then statistics and machine learning, which I'm going to end with what I consider a toy problem to illustrate some of these things. And the problem isn't toy because the underlying problem is a simple, easy, trivial one. It's because I just took a very, very naive approach to solving the problem as an illustration of some of these ideas. And you'll see that this naive approach actually ends up being of some value. So what do you need to know? What does everybody need to know? Well, in statistics and mathematics, there are a bunch of data issues that I'm going to talk about. You need to know probability. You need to know how to think non-deterministically. And for some of us, that's kind of problematic. And it's also something that in the past, computer science, depending on what branch of computer science you were in, might not really focus on. You know, queuing theory and all of those kinds of things, they're deep into probability. But a lot of the compiler design and stuff like that, my understanding is that all of that is all deterministic kinds of things. Statistical pattern recognition.
If you're lucky.
Okay. Statistical pattern, it may not act deterministic, but you're trying to make it deterministic. Statistical pattern recognition and machine learning I will briefly introduce. I'm not really going to talk much about evaluation. You guys have talked about that some. Network analysis and graph theory I think is really important, not just because you guys are dealing with networks, but because many problems naturally can be put into a graph theoretic format that allows you to do calculations that you couldn't have done otherwise. And I'll talk about that briefly. In computer science, of course, we've seen what almost all of this, and probably all of this. The things you need to know to do computer security. You need to know about protocols and APIs, how things work and how they interact. You need to know secure coding. You need to know how to make your code as secure as possible. And on the other side, how vulnerabilities happen. You need to know about operating systems and how to exploit them, databases and how to store and access large data sets and how to also exploit databases. You need to know about encryption, authentication. You need to be able to compile and decompile so that you can figure out what malware is doing. And you need to know about code obfuscation techniques because they don't want you to decompile this stuff. At first blush, computer security is getting the right-hand side correct. If you did all that right, we're done. And as we know, the best we can do, we can't do the right side perfectly yet. We still need something, and that's where statistics might be able to help. So here's my view. So from a statistician, what I think about is, first off, get a problem. And one problem is my system under attack or not? And you can view that as a classification problem. Class 1 is attack, class 0 is not attack. So, or an outlier problem. I observe normal stuff. Can you tell me when something not normal is happening? And so, what are we going to do? I'm going to collect data. So I'm going to collect data, possibly packets or packet headers, log files, maybe user or system activity. Somebody mentioned masquerade detecting. You might look at the applications the user uses or the things they type at the keyboard. You might look at system performance. If my system is acting a little weird, maybe that's evidence that something bad's happening. File and resource access. You might look at email in the content, in attachments, whether there are links or not, whether the links go to the place that the actual email says they go to. You might look at web activity. And when you look at all of this, what do you get? You get a lot of unformatted text. You get a lot of transactions or sessions or communications information. This is naturally represented as a graph. There's a lot of mixed, continuous, and categorical. Categorical is things like male-female or things like that are not numeric per se. There's a lot of streaming data. This stuff is coming at you a packet at a time every millisecond or so. And so you often need to make decisions based on just some things that you've seen recently. You can't look very far back in the past because there's too much data to process. As I've said, there's a lot of graphs and networks floating around in here. And for me, a network just means a graph with extra information on it. Maybe some information about the nodes or the edges. Massive numbers of observations. I've recently been working with Twitter data, where we're collecting, what the API will give you, which is some fraction, like maybe 2 or 3%, and only geolocated, and we're getting 11 million tweets a day. So 11 million a day isn't very much if you're looking at packets on a heavy network. But it's a lot of data to process. And it's also temporal. There's a lot of time involved, time series involved in this. The computer science approach, as I understand it, we've seen a lot of these things. You want to control known vulnerabilities through a bunch of things that restrict the usage in some sense. You want to detect the things you know about. match viruses, snort rules, things like that. And you want to detect bad things. So if you can decompile suspicious code or run it in a virtual environment or have a honeypot running or something like that, there's a whole bunch of things like this that you do. A statistician, instead, is data focused. So I will think in terms of, if I want to detect phishing in email, I need a bunch of email. I need some that have phishing attacks, and I have some that don't have phishing attacks. If I'm looking at network attacks, I need a sniffer on a network, and I need to collect packets. So the first thing I do is figure out what data I'm going to use to solve the problem, and collect the training data, analyze it, and I'll talk about these steps. Collect test data, figure out whether or not how well am I doing, and then I'm going to talk to the client. So as a statistician, I become an expert in lots and lots of things. Rakesh mentioned I wrote a book on computer security. I'm a computer security expert. I've done image processing. I'm an image processing expert. I do graph theory and networks. I'm working on brain graphs now. Now I'm a neurologist, for goodness sake. What I am is a statistician, which means that I know enough about the problem in order to solve some problems on it, but I'm not an expert in the domain per se. So I consult with experts to make sure that what I'm doing makes sense and that it solves the problem. And the answer, invariable, is not good enough yet, repeat. This is hard. And I'm going to talk about why collecting the data, and whether it's the training data or the test data, this is a very hard problem. For the purposes of collecting data for classwork, that's a different issue. But if you want to solve computer security problems, this data collection is going to be hard. And I'll talk about what some of the issues are. So how do you collect representative data for both normal and attack situations? And does the data you collected apply in the situation you're actually going to start using it in, or for other applications? If something changes, your user base changes, do you have to throw everything out and start over, or can you adapt what you've learned? Or do you not need to adapt? Okay? And how do you know these things? Does collecting the data change the data? Think about the computer masquerading problem. If you're going to detect somebody doing something on the computer that's not normal, and you tell a bunch of people, I'm going to monitor your keystrokes, how normal is their activity going to be after that? Possibly it's not going to be quite as normal. They're not going to watch as many cat videos, for example, as they normally would. The environment keeps changing. You've seen half a dozen slides that show X, Y, or Z is changing in time. It's always getting bigger or worse. And the threat is changing. And we have massive, complex data, and we want to do science. So how are we going to ensure that we can share the data, that other people can apply their approaches to the data, they can reproduce what we've done, so we know that what we're doing is valid? These are all really important and really hard problems. So let's punt and not worry about it. Most of these problems, if we will just simulate the data, we'll generate data, and we don't have to worry about where do we get the attacks and the normal data, because we can make it up. We can make this data. And this is not unique to this problem. Lots of people do this. The image analysis people simulate tanks in images and all kinds of things. This is very normal. So we're going to simulate the interactions with the outside. We're going to simulate our protected network. We're going to simulate the attacks, whether they're external attacks or internal attacks. So this sounds like a good idea. So DARPA did this in '99, and I want to say that I think they did a great job. I think they really did good work on this. And now I'm going to tell you there was all uses. There were a lot of problems identified. John McHugh wrote a paper that listed like 40 problems with the data. It's not as variable as real data. They didn't, real data has all kinds of TCP options, arcane things that nobody ever uses. Well, it turns out they do. It was too clean. There is a lot of crud in real data. There are packets that are fragmented that shouldn't have been fragmented. There's people put weird values in parts of the packet header. Who knows why? Anything that is in the requirements that is not actually forced by your infrastructure, just because it says you must do this, if nobody enforces that, people won't do it. So there's a lot of stuff that sort of break the rules in real data. It wasn't representative of anything. That was a problem. They didn't have anywhere near enough packets for a real network. And there were weird correlations. So I may get this a little bit wrong. My memory is notoriously horrible, but I believe that one of the attacker, they did all this in simulation, and one of the nodes that was being used to attack was used for many of the attacks. And it was always exactly the same distance away in the network they were simulating. And so the TTL values were always the same, time to live. And so if all you did was look for that, you could do pretty well. Well, there are reasons to consider TTL when you're doing computer security, right? You'd like to see if they're doing a trace route or something. But for the most part, TTL does not tell you this packet is an attack packet for some kind of denial of service or something. And the other thing that was huge is DARPA wanted to be able to ask, how do our methods that we're paying all this money for work for new attacks? So how do you generate new attacks? And they did some of this. They actually generated an attack that they thought could take down the internet. And it was actually a pretty good attack. But it was also pretty easy to defend against, it turned out. So, on the other side, we know a lot more. We can do a lot more in simulation now. We have a lot more knowledge of virtual machines and a lot more flexibility there. Maybe intelligent agents can help. But this probably isn't the way we want to go. Unless this is your area of expertise, in which case. Here's the other approach. Let's stick some sensors out there. So we can collect social media or websites or blogs if what you care about is what is the threat. So that's something out on the internet. You may look at email servers, logs, or firewall logs. You might sniff packets if you care about sort of this interface. Or if you're looking for the insider threat, you might look at log files. That's also for this stuff. File access, system calls, keystrokes, various things like that. So let's put these sensors on there, and that's a great idea. But anytime you try to do this, let me just tell you, do not ask the lawyers if you can, because the answer is going to be no, because privacy is huge. Okay, and you have to care about this. I joke about it, don't ask the lawyers. But you have to care about privacy. Even in the environment I am, where in order to use the systems you consent to monitoring, we cannot just willy-nilly monitor people. Okay? It's a violation of privacy. What about ground truth? You're seeing all the stuff that's coming through. How do you know which things are attacks and which aren't? How do you know that you can detect the things you don't know about if the only things you have to learn about are the things you knew? Okay? How are you going to solve that problem? The data is really complicated. It's unstructured. It's got, especially in this area, it's got a lot of noise. It's completely irrelevant noise. That Twitter project, we were doing a particular problem, and we would filter from 2 million tweets to 400,000 tweets to 6,000 tweets. So the filtering out of junk is of that order of magnitude. Whatever you do here, you're doing it on your network. How representative is that? And you've got a load on your resources. If you've got all these taps out there and you're filling up disks, that's going over the network, probably. And how do you manage that? And how do you share it? Privacy. You can't just give this stuff out. Even if you don't care about privacy, you figured out how to solve that problem, and so you can send it out. You're telling everybody you send it to a lot of stuff about your network. Do you want to do that? If you're starting to do this stuff, especially with keystrokes, you might have to do an IRB. Who the heck knows? And then I mentioned that question. So that's terrible. So what do we do? Well, simulations are still things to look at. We need to know more about anonymization and privacy. The statisticians do this all the time because they care about, they have all these medical surveys and they have to make sure that they're not giving out information about people's private things. And so there's a lot of stuff to be done. It's not a solved problem. Always, this is a statistician, always focus on problems for which you can get data. Don't focus on the problem that whoever's paying you really wants. Figure out what you can get data for. And then collect what you can. And there are ways to handle some of these privacy issues. If you're only looking at packet headers, and maybe you do a little bit of an IP anonymization just to protect people, right? Because, they're going to porn sites and stuff, and you don't want anybody to know they're doing that, or whatever it is. There are some things that you might be able to do. So, you've collected, or have a procedure for collecting, or have made up out of whole cloth all of this data. So now what are you going to do? So, what I'm going to do is statistical pattern recognition, or machine learning. To me, machine learning is statistical pattern recognition. The machine learners would disagree with me. They would say that there's overlap, but there is machine learning that is not statistical pattern recognition. And maybe they're right, but for me, this is it. What is that? It's feature extraction and selection. So you've got a whole bunch of data. Now you got to do something with it. You don't just take the data and throw some black box at it. You have to extract useful information from it. That's what the feature extraction does. And some of that you can do I can do as a statistician because some things are obvious. But you need expert information here. If I'm going to try to tell a missile from an airplane in a radar return, I need to know a lot about what radar returns actually mean. So I need an expert in radar to tell me that. Same thing here with computer security. Then dimensionality reduction, and one aspect of that is called manifold learning. I'll give you a little brief intro to that. So these are some keywords you can Google. Dimensionality reduction is critical because of a thing called the curse of dimensionality. I'll give you a really nice little look at what that means. And then I do classification or clustering or outlier detection or whatever. So we'll talk about those. So here are the features. So if I have packets, I'm going to look at the headers. There are IPs, there are ports, I threw in time to live. There's the handshake status if you're doing TCP. There's what protocol you use. There's all of the different options that are there. And so there's a whole bunch of stuff that you can do there. There's also time between packets. So you can start collecting a whole bunch of information from these packets. There's also the content. Is the content encrypted or not? Turns out that the content being encrypted does not mean that you should never look at the content. Charles Wright at Johns Hopkins did a paper where he looked at voice over IP, and it was encrypted. And he was able to tell who the he was able to tell males from females, and he was able to tell to some, was it males from females? That I'm not sure, but he was able to tell language, and he was able to pick out keywords if they were sufficiently long. So if you were looking for like intercontinental ballistic missile, he could tell you whether or not they had said that word in the thing. From encrypted traffic, and he never decrypted it. What was the key? The key was the way the protocol for the encryption worked is that you would take a chunk of information, a chunk of the speech, and you would encrypt that, which would typically change its size, because vowels, they can be compressed a lot, while fricatives, there's a lot of frequencies there, and so they have large packets. The size was kept. They didn't send equal sized packets. So just knowing the size of the compressed, which is what the encryption did, the compressed packets, compressed information, you could learn a lot about what was being said or things like that. That was really cool. Now, of course, it can be defeated, right? But the thing is that the people that do the encryption, they're thinking they have their set of criteria, and that set of criteria may not take into account things that you can use. So you might extract a bunch of things from content, and from email, of course. Email is fun because you have all these words. There's billions of words. And not only that, there's words and there's phrases, and nobody spells correctly, although now with the spell checkers and stuff, people are better. But there's also obfuscation attempts, right? So instead of saying Viagra, they would say V space, I space, etc. So there's a whole bunch of tricks that they use, and of course, as soon as you figure out what that trick is, they come up with a new one. So there's all this kind of stuff, and then there's links, and what kind of information do you get out of those links? And then there's the network. There's who's sending and receiving. Are these people in your address book or not? And have you seen things from them before or not? Things like that. And then there's attachments. So there's all these files that get stuck on there, and you extract information from those attachments, file type, things like that. And so that's the data that you collect. And now we need ground truth. If I'm going to tell you you've just been hacked, or this email is a phishing attack, I need to have data that corresponds to an attack, and I also have to have data that is clean, that doesn't. That's not completely true. There are what's called single class classifiers, where you'd only give it the bad stuff, but you're always better off if you can get the good stuff. There's normal versus abnormal. So you're looking for a legitimate user versus a masquerader, or an insider gone bad, or a never before seen activity, or things on your network, like was mentioned, the where they dither the times in the packets and things like that we saw earlier. You want to look for normal versus abnormal. But you have to know what normal is, and you have to have, you don't necessarily need to know what abnormal is, that's just something that doesn't match normal, but you have to get a good model for normal. So, some things to consider, some more things for you to Google if you're interested. We have imperfect knowledge in this area, right? Because you can only tag the things that you know, and you can only tag as many packets as you have undergraduate students to tag them, right? It's very tedious looking through millions and millions of records at things. Believe me, I've done it. So learning with an unreliable teacher is something to look at. There's some good papers on that. There you have imperfect ground truth. You know people have tagged things with the different classes, but you know they have error. Learning under imbalanced data, in our situation, there's way more normal traffic or good traffic than there is bad traffic. And so there's this imbalance, and you need to take that into account when you're doing this. There's also semi-supervised learning, where you can't tag everything. There's all this stuff that you don't really know whether it's good or bad, but you'd like to be able to use that stuff when you're building your class. You use the stuff that's tagged, but this stuff can also give you some information. So semi-supervised is something to look at. Finally, transfer learning. I talked about whether or not your thing is representative to somewhere else. Well, that's what transfer learning is trying to do. The data that you've got isn't perfectly representative of what's going to happen in the real world. You'd like to transfer that knowledge to the real world. And so that's called transfer. I know something about these things. I know less about transfer learning. So high-dimensional data. Each thing you measure adds a new dimension to the data. And so if you do text, you start with a word count histogram, most likely. There are other approaches, but the vast majority of text processing starts with a word count histogram. There are a lot of words, right? That's a huge dimensional thing. Packets, as I said, I could easily come up with 20 things to measure on a packet stream. And I'm sure you could come up with 20 I didn't think of. So the curse of dimensionality, my version of it is high-dimensional data is weird. It's not, your intuition is completely wrong. And the one way to see that is to think about this very simple problem. You take a square and you put a circle in it as big as you can so it doesn't go outside the square. And you look at what proportion of the volume of the square, the area in this case, is outside the circle. So you do that. Now you do a cube, put a sphere in there and look at the outside. Then you do 4-dimensional, 5-dimensional, 6-dimensional.